Till now we have completed the oscillators part. In the oscillators we have seen 5 oscillators, right? Out of 5, 3 were using for the low frequency and 2 were using for the high frequency. For the low frequency, RC phase shift, Hi friends, welcome back to Super Profs. Today we are going to start the power amplifier. Till now we have completed the oscillators part. In the oscillators we have seen 5 oscillators, right? Out of 5, 3 were using for the low frequency and 2 were using for the high frequency. For the low frequency, RC phase shift, 3-phase oscillator and Wien bridge oscillator, right? For the very high frequency, we are using Colpit and Hartley. Okay. So in the oscillator, again, if we'll discuss about the outcomes of all oscillators. So it was like, first we have seen RC oscillator. In the oscillator, we have seen the frequency of oscillation is nothing but 2 pi RC root 6. We have seen the relation between RF and Rin, that is 29 R1. Okay friends, this was the first one. Secondly, we have seen 3-phase oscillation. So in 3-phase oscillator, the frequency of oscillation was, this become root 3 over here, and this is 2 pi RC. No problem at all. In this case, the RF were 2 R1. Okay friends. Now let's come to the Wien bridge. In the Wien bridge, the frequency of oscillation was very simple, 2 pi RC, and the relation between resistors are RH is 2 R1. Okay friends. So we have seen one question based on Wien bridge. That was the gate problem in which they were. Hi friends, welcome back to Super Profs. Today we are going to start the power amplifier. Till now we have completed the oscillators part. In the oscillators we have seen 5 oscillators, right? Out of 5, 3 were using for the low frequency and 2 were using for the high frequency. For the low frequency, RC phase shift, 3-phase oscillator and Wien bridge oscillator, right? For the very high frequency, we are using Colpit and Hartley. Okay. So in the oscillator, again, if we'll discuss about the outcomes of all oscillators. So it was like, first we have seen RC oscillator. In the oscillator, we have seen the frequency of oscillation is nothing but 2 pi RC root 6. We have seen the relation between RF and Rin, that is 29 R1. Okay friends. This was the first one. Secondly, we have seen 3-phase oscillation. So in 3-phase oscillator, the frequency of oscillation was, this become root 3 over here, and this is 2 pi RC. No problem at all. In this case, the RF were 2 R1. Okay friends. Now let's come to the Wien bridge. In the Wien bridge, the frequency of oscillation was very simple, 2 pi RC, and the relation between resistors are RH is 2 R1. Okay friends. So we have seen one question based on Wien bridge. That was the gate problem in which they were, doubling the time constant. the time constant. Time constant means in the VN bridge we are having two branches. In one branch you have capacitor and resistor connected in series, and in another branch the capacitor and resistor, they were connected in parallel circuit. So they have their own time constant. Let's take it type E, and they also have tau s. So if you are doubling the tau constant, definitely your frequency will become half of this, just half of this. Okay. Now after this Wien bridge, we have seen two LC oscillators, Colpit and Hartley. So the fourth one, Hartley. In the Hartley oscillators, the condition was tau output, tau input. This is the condition I gave you to remember. Okay. So tau output is, we are using the Hartley, so L by R kind of thing should be there. So this is L2 by RF. Over here L1 by R1. This is relation. Is it okay? And if I'll talk about the frequency of oscillation, so it will be 1 divided by 2 pi under root of L equivalent of C. Okay. When RC is there, there is no under root over RC. Okay. But whenever LC will be there, you will be having under root over there. Okay, friends. Now, at last we discuss about the Colpit. The same thing, tau out equal to tau input. Now the tau is RC. Is it okay? So here I'll take C2 RF. Here I'll take C1 R1. Okay, friends. And the frequency of oscillation in this case will be 1 by 2 pi L C equivalent. I hope this all formulas are clear to you now. Okay. Now let's start the power amplifier. So what is the power amplifier? So friends, as we discussed earlier, this is not important topic for us as per the GATE exam, because last time we got the question in 1999 from power amplifier. Okay, so this is not that much important. But we have to discuss it because this is the part of syllabus. So power amplifier are basically that large signal amplifiers. These are the large signal amplifiers. Okay, friends. So if we'll talk about this power amplifier in particular, so large signal means in this diagram, if you'll observe, see, this is the simple mic and speaker I'm taking over here. This is the input stage, mic is over here. Okay, and you are speaking, the input is. Okay, what mic will do, mic is like sensor. It will sense your voice and convert into electrical signal, very small electrical signal. That signal will be, in this stage will be amplified. C, CC, whatever amplification you are introducing over here, this is amplifier part, okay. So your small signal coming over here from the mic will be amplified over here, and here we will introduce the power amplifier. The power amplifier. Now this is very small signal here, but what power amplifier will do, it will take this small signal and make it very large, so it can run the speaker. Okay, here speaker is there. So it can, sorry. So it can run to this speaker. Okay, so this power amplifier will be biased by DC source. So this small signal will become very large, or I can say it will be powered by this DC supply, and this will be AC definitely. At the output stage it will be AC, and this AC will run to this speaker and will get loud voice over here. At the input stage the voice were very small, but here it's become very loud. Okay friends, so the AC, the output of this power amplifier, this is the entire thing we can consider the power amplifier. Though we know that the power amplifier see, this is the power amplifier, it will contain amplifier, and this is the power amplifier. Here they will signal in this stage the power amplifier will amplify again, or I can say the increase the power. So at the output stage we are getting high ACs. So in the power amplifier at the output stage the current will be very high and voltage also will be very high. So AC current and AC voltage both will be very high at the output stage of power amplifier. Is it okay friend? So based on the application, the power amplifier is classified into 4 categories. Class A amplifier, Class B amplifier, Class AB and Class C amplifier. Okay friends. So what is the Class A amplifier? What is Class B, Class AB and Class C? Class AB means whatever input you are giving, if you are giving this input, at the output also you will get very large signal, but the same signal whatever you are applying at the input stage. Is it okay? There is no distortion over here, or ideally the zero distortion. So practically we were getting distortion, definitely will get the distortion, but for Class A amplifier this is the 360 degree, means whatever you applied you will get the entire thing. The 360 degree of that you will get, means 0 to 2 pi you will get the entire waveform. This is in Class A amplifier. Is it okay? So Class A amplifier, it will consume power, high power. The power consumption by this Class A amplifier is very high, so we are not using Class A as per power amplifier. This is not used for power amplification. Instead of this Class A is using for voltage amplifying. So this is voltage amplifier. The Class A amplifier we are not using for the power amplification. We are using Class A amplifier for voltage amplification. How you can remember this? This is A. Okay, so you have to take inverse of this. So you will get V and V for voltage. Is it okay? This is the trick I am giving you for remembering. Because if they ask the question, they will simply ask, they will give one table. In the table Class A amplifier, Class B amplifier, C and AB and their applications or their working operation, phase angle, like this. So this is about the Class A amplifier. We will discuss in detail also. This is the brief I am giving you before starting. So in the Class A amplifier, the entire amount of the input you will get at the output. So I can say the 360 degree of the input you will get at the output. But if I'll talk about the Class B amplifier, and one more thing friends, I'll show you in terms of load line. Okay, so it will be better clear to you. These are the characteristics of BJT. Is it okay? You are familiar with this. Like this. Like this. Like this. Okay? And now I am drawing the load line over here. Let me draw the load line. This is the load line. Okay? So for the Class A amplifier, where should be the Q point located? Tell me. Where should be the Q point located over here? It should be there in the middle. Exact middle. Let's check this is the middle. So for Class A amplifier, what you need, you are applying this input, you want to get the entire output. Okay, so you should be having the Q over the mid of load line. As we discussed earlier, when the Q point will be there on the midpoint of the load line, then only we'll get undistorted output. Okay, in the stability of BJT, we have seen that we were changing the Q point there. We were keeping in the middle, we were keeping near to saturation, near to cutoff, and we were getting the output. The output was clipped by if you were taking the Q point at the cutoff region or saturation region, kind of we have seen there in the BJT. Similarly, we'll use the application of that thing only in the class B amplifier. So this if you keep this Q point over here, so this is class A amplifier, means the entire thing you will get at the output. But for the B amplifier, your Q point will be near to cutoff here. The B will be near to here or here. It may be a two condition, near to saturation, because this is the saturation and this is cutoff. So for class B amplifier, it will be over here. So 1/2 of the input will be 0. If you are applying input over here, so you will get output only 1/2. Here you applied input. Let's take. We have seen this earlier, right? Here I applied the input. This entire positive half will be mapped over here. But below this entire thing is cut off, means 0. So it will become like this. So we will get in this way. Okay. Wait a minute. Let me clear some part. So for the B amplifier, where will be the Q point located? The Q point will be near to cutoff or near to saturation. Is it okay? So what will be the output? In this, it will be for 180 degree. We'll get the 180 degree at the output. 180 degree of the input only. Means only 1/2 will get at the output. So output will be like this for class B amplifier. Is it okay, friends? I'm sorry. So class B amplifier, we were discussing for the class B amplifier, the output will be like this. Definitely it will be distorted by some like this. You can see over here. It will be distorted later. I'll show you. Let me draw again. Output characteristic of the BJT. No problem at all. See. Now here I'll take the AC load line. This is the load line. For the Q point at the middle, you have A amplifier, class A amplifier. Over here, you have class B amplifier. Now we were discussing, or we'll start with class AB amplifier. As this is taken AB, means it will be in between A and B. Over here, it will be like this. So for class AB amplifier, the Q point should be located in between the Q points of A and B amplifiers. Is it okay? So tell me one thing. In the distortion, in terms of distortion, if I'll talk about, in the class A amplifier, distortion will be minimum. Okay. In class B, the distortion will be very high. In the class AB, it will be moderate because it will be in between of them. It will be less than B, but higher than A. C. If I'll talk about the waveform over here, it will be some kind of like this. We'll not get the full waveform, but we'll get the greater than the half. So here, in terms of phase angle, it will be in between 180 degree to 360 degree. We are not going to get 360 because 360 is for A, 180 degree for B. So definitely for AB, we will be in the middle of this. Is it okay? Now if I'll talk about the class C amplifier, for the class C amplifier, we'll choose the Q point over here, below cutoff. Over here we'll choose the our Q point. In this case, you will suppose you will apply the input over here, you will get very minimum amount of input at the output like this. Very minimum. So distortion in the class C amplifier is very high. Highly distorted waveform we'll get. But this is advantageous. So that's why we were discussing about the class C amplifier. This we use for triggering. Okay. So friends, now I'll come to some parameters related to this part. Let me show you. In the amplifier, the most important thing is conversion efficiency. At the output or at last we were calculating this one only. What is the conversion efficiency of all these 4 amplifiers? Okay. So first let me tell you what is the conversion efficiency. Denoted by eta, right? And conversion efficiency is nothing but the AC power, AC output power, I can say. AC output power divided by DC power supplied. DC power supplied to input. See friends, we have seen in the diagram, the power amplifier is connected with the DC biasing. Okay, this power amplifier will get amplified version of the input, but here it will increase its power, so it can govern the speaker over here. Okay friends, so this power amplifier using some power by this DC biasing. So DC power supplied to input. Here it's taking some power, and here this AC has its own power. So your efficiency is AC output power divided by applied DC power. Is it okay? Into 100. So it will be in percentage. So this is the conversion efficiency in percentage, that eta is nothing but power AC divided by power DC into 100. So eta in percentage. Is it okay? Okay friends, now we'll see the figure of merit. Now we'll see figure of merit. These are the basic terms. So this is the maximum power dissipation through the BJT. Inside of the power amplifier, it is made up by BJT circuits, right? So we are applying the input DC, we are giving the power. So the power will be dissipated because of the various elements, resistive elements, right? So the power dissipation through the BJT or by the BJT divided by the AC power delivered to the load. PAC delivered to the load. Okay friends, are you getting me? So I can say like this is the maximum power dissipation divided by maximum AC power. This AC power transferred to load and this power dissipated by BJT circuit. Okay friends, so this is the figure of merit. Now tell me one thing. The figure of merit for the good conversion, what should be the figure of merit? It should be small or high? It should be very small. Why? The power consumption by the BJT should be minimum or not? Yes, it should be minimum. And if it should be minimum, so this entire thing has become 0 or very low. Okay friends, so these two terms are very important, figure of merit and the efficiency. Okay friends, so as I told you, class A amplifier were using for voltage amplification. Voltage amplification. The B were using for audio. Wait a minute. This was the audio frequency power amplifier. Audio frequency power amplifier. Okay. The class A was voltage amplifier. Okay. Class B was audio frequency power amplifier and class C is untuned power amplifier. This is untuned power amplifier. Sorry, this is AB. And if I'll talk about the C, it is tuned power amplifier. Tuned power amplifier means in the radio range or radio frequency amplification we are using it. Radio frequency power amplification. Okay friends. So in the radio frequency we are using C no problem. For the untuned power amplification, we are using AB. For audio frequency power amplification, we are using B. And for voltage, we are using A. Is it okay? Now, will come some circuit of A and B and all this. So, if I'll talk about the class A amplifier now. So, in the class A amplifier, the first one is direct coupled class amplifier. Direct coupled. Direct coupled means, suppose we are taking one BJT over here. Let's take like this, the circuit is. Okay, let me draw the circuit. This is RB over here. Here we are applying some input. Okay. This is connected with VCC. Perfectly fine. Here I'm taking VCC. So direct coupled means this RC become your RL. We are introducing our load over here in the collector terminal. So directly we are getting at the output stage what is the amplification. That's why we are calling it the direct coupled amplifier. So how to proceed now? In the class A amplifier, we have chosen the direct coupled amplifier. Now this is the circuit given over here. So this is the circuit in which AC, DC both are present. So we have to do AC analysis and then DC analysis. I'm not going to do this analysis over here. So the concern is, in the class A amplifier, the circuit is given. What we'll do now, we'll do AC analysis and DC analysis. If we'll do the DC analysis, we'll get the equation. Let me take direct value minus RC VCE. Definitely there will be relation between VCE and IC because between them only we are drawing the load line. So this is the DC output. Now if we'll take the AC load line or yes, in terms of AC load line, it will be, the relation is like IC minus ICQ equal to minus 1 by RC VCE minus VCEQ. Okay friends. So this one is not important. That's why I'm not going deep inside. But in the class A amplifier, how will be the output? See, you can easily observe now. Let me draw this diagram. This diagram will come after doing the analysis, DC analysis, AC analysis, then we'll draw the load line, and based on that load line, we'll locate the Q point in the middle because this is the class A amplifier, and we'll see how the amplification is going on. We will talk about the particular Q. So this Q is nothing but VCE and ICE. Let's consider Q also, ICQ. This is the Q point, so that's why we are taking Q and Q. But in general, the Q point is nothing but the relation between VCE and IC. Okay, perfectly fine. Here is definitely VCC, and this it's IC, and this is VCE. The value of VCE when current is 0 is become VCC. Okay, and here when VCE is 0, the IC become VCC by RC. VCC by RC. This is the DC load line we have seen earlier, right? Now friends, how we are applying input output, how we are getting the relation and all. So let me show you. Let me change the color. Okay, fine. Over here, now you have this range, right? You have this range, input output range. Perfectly fine, no problem at all. Now let me draw the circuit, the waveform. This is the input waveform, suppose you have given, right? This is I mean 0, this is I max, and this I max is 2 times of ICQ. Can I write like this? ICQ is the current level, this current level. So this is the 2 times IC max. I max is the 2 times of ICQ. So this entire thing should be amplified or not. This point will come over here and will map at this point like this. This point will come over here and will map over here. Okay, fine. This point will come over here and will map like this. Okay. So this portion will get over here like this and like this. So entire thing will get. Okay. Now, so this is the voltage, so I can take this Vm. This is V minimum actually, and this is V max. So V max will be over here. Okay. So this is the waveform for direct coupled class A amplifier. No distortion we are getting over here. Is it okay? Q point will be located in the middle of the load line. Why? Because we discussed earlier, in the class A amplifier we are getting 360 degree of the input. So definitely the Q point should be located at the middle of the load line. Okay. When the Q point will deviate, there will be distortion in the circuit or in the output. Okay. Now the most important thing is conversion efficiency. The conversion efficiency. Conversion efficiency we have seen. It's PAC divided by PDC. Is it okay? And in terms of, suppose in percentage we'll talk about, so we'll multiply with 100. So power, AC power delivered and the DC power supplied to the BJT. Okay, this is the conversion efficiency. Now we'll take the AC power, PAC. What is the PAC? Wait, let me change the color. PAC is nothing but IRMS into VRMS. Is it okay to you? Now, what is the IRMS? IRMS is nothing but max by root 2. And this is nothing but max by root 2. So finally you have, sorry, this is IM. Finally you have VM IM by 2. Is it okay? Now what is VM? The diagram we have seen earlier, in that diagram, the VM is nothing but VCC minus V min divided by 2 or not? Tell me. We have seen the diagram. In the diagram it's like this. This was the minimum level or the maximum level, Vmax level. So what we are taking Vmax. This thing was Vmax. This thing is Vmax. So this is what we are doing, Vmax minus Vmin. So this entire thing I'm getting, and I'm dividing this thing by 2. VCC minus Vn by 2. So I'm getting Vm. Okay friends. And what is Im? Im over here is given by ICQ. Okay. Now friends, ICQ is the maximum current. Yes, we have seen. Because this was the middle current ICQ and this is the level of Imac. So this is equal to ICQ. Okay friends. Now if you'll multiply these two quantity, or if you'll put the value of Vm and Im over here, you will get like VCC minus Vmin divided by 2 into ICQ. Okay friends. Now finally what we are getting is, let me show you directly over here. When we'll solve that, we'll get VAC equal to VCC minus Vmin divided by 4 into ICQ. No problem at all. Now if I'll talk about the DC power, the DC power supplied by the biasing. The biasing voltage is VCC and the current by biasing is ICQ. So definitely this is your PDC. Now I'm talking about the conversion efficiency. So the conversion efficiency is this upon this, VCC minus Vmin ICQ divided by VCC minus ICQ. Sorry, this is in multiplication. ICQ will cancel out this, and finally you are remained with efficiency in percentage is 1 minus Vmin divided by VCC like this into 100. This is the percentage. Okay. So, and where is the 4? This 4. Here is the 4. So it will become, let me take on the fresh page, wait a minute. So friends, the eta is become now 1 minus V min divided by VCC into 25%. 100 divided by 4 will become 25%. So this is the efficiency given in the percentage. Okay friends. Now if V minimum is 0, suppose. Let's take V minimum is 0. And definitely we keep minimum is 0. So this will become 1 minus 0 into 25%. So this is 25% over here. Okay. So this is the maximum efficiency of class A direct load couple amplifier. Class A direct load coupled. This is the maximum frequency. Efficiency. Okay friends. Now what V mean is 0. If you remember that load line, here at this stage we drawn the our voltage, right? It was V min this. So V min was coming near to 0. This is the 0. This is VCE. VCE starting from the 0. V min is nearly 0, right? And it will be possible only when this Q point will be at middle. Otherwise, this V min will go in negative region. Okay, so you need minimum V min, or you need the maximum efficiency of the class A amplifier direct load couple. So you need to take the class direct couple amplifier. The maximum efficiency will be 25% when the Q point will be located at the middle. Okay friends. Now, if I'll talk about the figure of merit, let me talk about the figure of merit also. Figure of merit. Now figure of merit, the formula we have seen is, let me show you again. The figure of merit formula, F is equal to PD max divided by PAC max. Is it okay? This was the power delivered and this was the power dissipated, if you know. Okay, so we'll see the figure of merit for this circuit. So let's find out PD first, and this is the dissipation power. Dissipation power means the power delivered by the biasing, and it will be definitely VCC into ICQ at any point. Okay, because this is the power delivered by the load, by the source, and it will be dissipated by the source. Same, or this same power will be dissipated by BJT circuit. Whatever power is delivered by source, the same power is dissipated through resistor or through circuit. So PD max is clear. Now, and maximum AC power supplied is, I'm talking about AC power maximum supplied is, it will be definitely VM IM by 2, VRMS IRMS. Okay friends. Now, okay, perfectly fine. So here VM is nothing but VCC, because for the maximum power you need to take V min equal to 0. If V min is equal to 0, then VCC is nothing but VM. Okay friends. Now if this is VC and this IM is nothing but ICQ divided by 2 is your this, now you have to calculate figure of merit. What is your PD max? Your PD max is VCC ICQ. What's your this? The VCC ICQ divided by 2, this 2 will go up and this will cancel out. So you are getting figure of merit for class A amplifier whose efficiency is 25%. The figure of merit is 2. Okay friends. So this is very less efficient direct coupled. So we are using mainly the transformer coupled class A amplifier. Class A transformer coupled. Let me draw the circuit. For the class A amplifier, the circuit for transformer coupled is, this is RE, CE, RB, like this. This is the transformer coupled over here, and here I am connecting RL. So in the direct couple, the load resistor was connected in the C collector, but here it's not directly coupled, it's transformer coupled. Between the load and collector we are having transformer. So this is VCC over here, everything is given. This is RB, over here I apply V in, capacitor is given over here. This is the drop VBE. This is the transformer couple. Okay. So here in this case, what we are doing, we are connecting one transformer, and here in the transformer we are connecting the load. But in the direct couple we are using RC over here. So what is the advantage of transformer couple? See, it will increase the efficiency, as well as what it will provide the DC isolation. DC isolation means at the output stage there will be no DC, only complete AC will be there. See, when the C was connected, when the load was connected directly into collector, some DC part whatever coming from the inside were, introducing in this also the load, and this was undesirable. We do not need any DC over here, we need only AC. At the input AC, at the output both are AC. But in this case, the DC will be isolated over here and entire AC will come. This is work on the flux, right? Principle of flux linkage. So we'll get only IC over here. So provide the DC isolation only. Also, okay. So if we'll talk about the load line and the diagram in this case, definitely the Q point will be at middle. But what will happen over here, this will come for entire cycle now. Now your V minimum will be this point. This is V minimum. This line will become V minimum over here. Okay. So I'm not going deep inside. Now directly I'm coming to the conversion frequency. Conversion frequency. Okay. Again, the conversion frequency formula is, tell me, this is PAC divided by PDC, I can say. This is the power supplied and this is the AC power supplied to the load. Okay. So directly I'll come to the efficiency formula, and efficiency in percentage over here is nothing but V max, this is V, minus V minimum divided by V max plus V minimum into 100. Okay friends, and it will be by 2 over here. So this entire thing, let's K into 50%, like this. So when V max is equal to V min, you will get 0 over here. Okay, so this is not possible. Now what about the figure of merit? Figure of merit for this circuit is same as we calculated for the direct couple. It will be 2 over here. Okay friends. Now we'll see some more parameters related to this. So now we'll switch to the class B amplifier. Okay. So for class B amplifier, I'll show you the circuit diagram and efficiency. Okay. The push-pull arrangement for this is very famous. Push-pull amplifier, I can say, in the class B. And the push-pull amplifier is using 2 NPN transistors connected in this Q1. Over here it's Q2, they are connected like this. This is transformer primary. Here transformer secondary, like this. Here the load is connected. This again primary stage. Now in this type, in this manner we are applying input. We are using transistor, transformer stages both sides, right? Let's take it B1 and B2, and one more thing, this is center taped. like this. This is the push-pull arrangement. So briefly I am telling you what will happen. This current will link to this current, this voltage will link to this. So here it will make like V1 plus minus V2. At the first half cycle it will make. Because of this, this Q1 will work, this Q2 will not work. It will be in complete reverse bias because negative V2 we are applying over here. So we'll get the current in this circuit only. So because of this current, this flux will linkage again over here, and here also we'll get something. Okay, in the negative half cycle, it will be plus and it will be minus. In this case, this one will work. So entirely we are getting this current, and this current is due to for this. Suppose this is I1 and this is I2. Okay friends. Now let me come to the direct diagram. So see the diagram. This is IC and this is definitely VCE. Okay, and let's take direct load line. I have taken load line. Where will be the Q point? Definitely over here, because this is the B in we are talking about. Okay. Okay, Q is selected. No problem at all. Now here is the input applying like this. Like this, input applying. You apply the entire input. Like this, I applied the input over here. This will be distorted now. So this is your point. So it will come like this over here, like this. This entire thing will come over here in this way. It will touch to this. Like this it will come over here. So see, the half portion of the waveform is distorted. This is plus half, minus half is missing in the output. So this is V min and this point is VCC. Okay friends. So if I'll talk about the efficiency, conversion efficiency, the formula is again the AC power delivered and the DC power supplied. Okay friends, so in this case, if we will solve these two things, what we will get is, wait a minute, the percentage of eta is nothing but 1 minus V minimum divided by VCC into 78.5%. 78.5%. So when V in will be 0, in this case, when V in or V minimum, sorry, this is minimum, is 0, you will get maximum efficiency, and that is 78.5%. So definitely, at your load line, your input should be, or your V minimum should be this line. So it will be not distorted. Okay friends. So till now we have seen for the transformer direct coupled circuit, direct coupled. In the direct coupled, the maximum efficiency was 25%. This was class A amplifier. Then we have seen the transformer coupled. Transformer coupled. So the maximum efficiency was 50%. Now we have seen the push-pull transformer. Push-pull transformer amplifier. In this case, the max efficiency we are getting 78.5%, and this belongs to class B amplifier. Okay friends, now next. And if I will talk about the figure of merit for push-pull, the figure of merit is given by 4 by pi square. See, very minimum. In these two cases, the figure of merit was FOM was 2 and 2. Sorry, yes, for these two cases, the figure of merit was 2, but for this it is 4 pi square. Pi is 3.14. You will take square. It's nearly 10. So 4 by 10 and something. 0.4 we are getting over here. Okay, and we earlier discussed the figure of merit should be minimum or smaller for better conversion. Okay friends. Now some advantages are given over here. The efficiency is, wait a minute, let me erase this. So the biggest advantage of the class B amplifier is the efficiency is greater than the class A amplifier. Okay, and what is the disadvantage? The disadvantage is circuit is bulky because we are using over here two transformers, sorry. Now let's come, what is crossover distortion over here? Crossover distortion. Friends, we are using in the center tab or in the push-pull, we are using two transistors. Okay, and we know for the transistor there is a minimum barrier potential, and that is 0.7 VBE. Before this point, the transistors will not work. If you are applying 0.6 volt at the VBE junction, it will not work. This is kind of diode. Diode needs 0.7 drop across it. Then only it will run. Okay. Similarly over here also. So let's take one transistor is working because one by one transistors are working. Okay. So let's take the one transistor is working. When it will be turned off, suppose this is the transistor Q1, when it will be turned off immediately, what I mean by this Q1 is, this is the wave because of Q1 on. When here at this point the Q1 is going to off, immediately we will not get the output. We will get 0.7 because of the 0.7 means for the second Q2 you have to give 0.7, then only it will work. But we are crossing 0, we will move 0.1, 0.2, 0.3 up to 0.7. So up to 0 to 0.7, the current at the output will be 0 definitely. And then it will come like this. Again 0.7 like this. So it will be continue like this. So this is nothing but the crossover distortion. Crossover distortion, COD. Okay. Now let's come to the class C amplifier. So the circuit diagram of the class C amplifier is like this. This is VCC over here, and this is the tuned circuit. This circuit is the tuned circuit, and this will act as a load. Tuned circuit, we call it, and will act as a load. Okay, friends. So this is the class C amplifier, and the class C amplifier is not used for the audio amplifier. Who will use for the audio amplifier? For the audio amplifier, we are using class B amplifier. Okay. Now, in the class C amplifier, the output will be like this. Let me show you. Wait a minute. If I am taking this V in like this, for small portion like this, I'll get the output. Only this I'll get at the output because the maximum distortion is coming over here, right? So at the output I'll get this much of the portion only, like this. Only this much. Below 180 degree. Below 180 degree, the phase. For the class A, okay, later we'll discuss about this. So this phase angle is below 180 over here. Nah? So this phase angle we also call the conduction angle. Means for this reason only it will conduct. Right? So what is the efficiency? The point is, in the class C amplifier, again we'll see the efficiency. We are not discussing about entire circuit. Okay? So let me show you, wait a minute. The efficiency of this will be, no, I do not have the efficiency for this class C. Okay, friends. So now briefly we'll discuss about each and every class A amplifier, class B, class AB, and class C. For the class A amplifier, what is the conduction angle? 360 degree. Means the entire cycle will come at the output. For class B, the conduction angle is 180 degree. Only half cycle will come over here. Half cycle. Here the full cycle. What is class AB? Here the conduction angle is in between 180 degree and 360 degree. Okay friends. In the class C amplifier, the conduction angle is less than 180. If I'll talk about the distortion is very high in C, then B, then AB, then class A amplifier. Okay, AB is the stage between A and B. So suppose in this we are getting full. So in the AB we'll get 2/3 of full. In B we'll get half. And in C we'll get below half. Okay friends. Now the question is given. Let me take one question. Wait a minute. So the question is given. In the case of a class C amplifier, means for class C amplifier, 4 options are given. The question is, in the case of class C amplifier, the load must be. Option A is given pure resistive. Option B is given parallel tuned circuit. The option C is given series tuned circuit. And option D is given none. So tell me, for the class C amplifier, what is the load? We have seen the tuned circuit over there, right? Like this it was. So this is the parallel tuned circuit. Definitely the option will be B over here. Now the next question is given. Crossover distortion behavior. Crossover distortion. Crossover distortion is the characteristic of A amplifier, B amplifier, AB amplifier and C amplifier. So in the B amplifier, the answer is B amplifier, because in the B amplifier we are using 2 NPN transistors like push-pull arrangement. So because of both of them we are getting distortion like this. These are the distortion. Instead of this original like this, we are getting some distortion over here. Is it okay? So distortion is the property. Fundamentally, distortion is the property for B type of amplifier. So if I'll talk about class A amplifier again. So class A amplifier was the voltage amplifier, right? And the conduction angle was 360 degree. Okay. Now it was 3 types of actually RC coupled, and we have seen direct coupled, and one more thing is transformer coupled. Okay friends, the RC we did not see. Why? Because the efficiency over here is only 5%. Here it's 25%, and in the transformer case it's a 50%. So sometimes they can ask the question based on this also. Okay. So in the class A amplifier we are having 3 circuits: RC coupled, direct coupled and transformer coupled. For the RC coupled the efficiency is 5%, for direct coupled the efficiency is 25%, and for transformer coupled it's 50%. Now if we'll talk about the class B amplifier. So class B amplifier, the conduction angle is 180 degree. Okay. And it was also 2 types. The circuit was push-pull arrangement, and secondly is complementary symmetry pair. Okay. And the maximum efficiency over here was 78.5%. Now if we'll talk about the class C amplifier, class C conduction was below 180. Okay. Class A amplifier was voltage amplifier, class B amplifier was audio frequency amplifier, and class C is the tuned, because we were using the tuning circuit, tuned power amplifier. Okay friends, so this is all about the today, and we'll meet in the next. We'll discuss some more about the power, then we'll cover some more miscellaneous topics like 555 timer and all. Okay, we'll meet in the next. Till then, take care and bye.